Hello everybody, I hope you're all doing well. So we're going to be solving another problem on the idea of collisions, and in this problem we will use a combination of linear and angular impulse momentum techniques. Okay, so here is the problem. In this particular problem, I have an inverted pendulum. Okay, an inverted pendulum, which is in a state of equilibrium, and there is a ball traveling and then striking the pendulum as shown. Okay, so let's first start off with the inverted pendulum. So here is the pendulum, fixed pivot. Okay, and then the length of the pendulum. Let's assume that the length is going to be 1 meter. Okay. So let's say that L is equal to 1. Okay, and then this is the bob of the pendulum, which I'm going to call as P. Okay, now there's a ball that is traveling, and this pendulum is at rest to begin with. There's a ball traveling with a certain velocity, and this is striking the pendulum as shown. Okay, so here's a ball, and let's say that I'm going to fill it with a different color. Okay, alright, so here is a ball that is coming and striking the pendulum. This is the direction of the velocity of the ball as it strikes the pendulum. Okay, so this ball is traveling in this particular manner. Okay, let me extend this line here because I want to make use of this line to show you something else. So this is the line of the velocity of the ball, and let's say here is the velocity of the ball. Okay, so this is the ball B, and the velocity of the ball right before it impacts the bob of the pendulum is 5 meters per second. Okay, so this is going to be velocity of the ball, which is 5 meters per second, and let us say that the angle between this line that I have just drawn and the vertical is 45 degrees. Okay, so let's say that this angle here is 45 degrees, and this line that I have just drawn is a line through which the ball is, along which the ball is impacting the bob of the pendulum, and so this is called as the line of impact. Okay, so this line here is called as the line of impact. Okay, so this is the line along which the ball is traveling and then striking the pendulum, and let's call the pivot of the pendulum as the point O. Okay, so pendulum is P, and then the ball is capital B, and then I'm told that the mass of the pendulum is 1 kilogram. Okay, so given that MP is 1 kilogram, mass of the ball is also given to me. Okay, and this is going to be 2 kilograms. Let me write my B properly. Okay, and one more information that I'm given is that the coefficient of restitution during the duration of impact is 0.45. Okay, so the coefficient of restitution, so given coefficient of restitution, okay, between the ball B and the bob P is 0.45. Okay, so coefficient of restitution is a term that I have defined in my lecture notes, and this is something that I would like you to go through and then see. We're going to make use of that in our problem today. Okay, and this is typically called as E, little e, and so little e is 0.45, and by definition little e is a ratio of the relative velocity upon impact to the relative velocity right before impact. Okay, so by definition E is the relative velocity right after impact okay, divided by the relative velocity right before impact. Okay, and one more thing is that this coefficient of restitution is also called as the normal coefficient of restitution. This is because this is defined only along the line of impact. Okay, the definition of E or the value of E given here for us. So the value of E for us is defined for all velocities along the line of impact. Okay, so you can say that this relative velocity right after impact and relative velocity right before impact, these are all velocities, these relative velocities are along the line of impact, okay, or in the direction of impact. So this is the definition, okay, and we're going to make use of this, and as I said, my lecture notes, which I'll have uploaded, I would have had a longer derivation of what the coefficient of restitution is. So we will be skipping that derivation in this problem, but we will be making use of this idea here. Okay, so once again, I have a pendulum here which is initially at rest. Okay, there is a ball that is coming and striking the pendulum. Here is a line of impact between the pendulum and the ball. What am I supposed to find out? Okay, find. Okay, find all the post-impact velocities. Okay, that is find the velocity of the pendulum right after impact, find the velocity of the ball right after impact. Okay, and we will also try to find the impulse of the contact force. Okay, so that's one thing that I want to find. Second thing is the impulse of the contact force between the ball and the bob. During the duration of impact. Okay, okay, so this is the central premise of this particular problem, and what is our solution strategy? Okay, so I have this pendulum sitting there minding its own business. There's a ball coming and striking it. What's the pendulum going to do? There's going to be a collision event taking place, and right after impact has taken place, the pendulum is going to start trying to rotate because it has been upset from its equilibrium position. I mean, this is the pendulum staying vertically up is called as an unstable equilibrium position, because even a small gentle nudge is going to take this pendulum and then let it start swinging all the way away from its equilibrium position. So that is called as an unstable equilibrium. So the pendulum is at this uneasy position, unstable equilibrium position. The ball strikes it, the pendulum is going to start swinging. I want to find out what is the velocity of the ball right after impact has taken place. What is the velocity of the pendulum bob right after impact? Okay, so that's something that I want to specify here. This is right after impact. Okay, and an additional piece of information given here is the coefficient of restitution in the direction of the line of impact. Okay, so this is in the direction of the line of impact. This is a material property. This is typically something that can be obtained by means of experimentation. Okay, all right, so let's go to the problem. Before we start the problem, okay, we need to see what type of an impact this problem is. Okay, so there are typically two types of impacts. Okay, so types of impacts or types of collisions. Okay, there is a direct central impact. Okay, in direct central impact, the pre-impact velocities of the impacting bodies are along the line of impact. Okay, so if the pre-impact velocities of the impacting bodies are along the line of impact, okay, then it is called a direct central impact. Okay, so that's one thing. So let me just underline these things. Here is one, then here is another one. Then I have what is called as oblique central impact. Okay, if even one of the pre-impact velocities of if I if I consider two bodies impacting, right? Let me put it this way. Even if one of their velocities, the pre-impact velocity, is not along the line of impact, then such a collision is an oblique central impact. Okay, so if the pre-impact velocity of even one of the impacting bodies is not along the line of impact, then it is an oblique central impact. Okay, so this is the second one. And of course, when we go to rigid bodies, you will have something called as an eccentric impact. Okay, we will talk about that when we get to rigid bodies. So this is typically for particles. Okay, so particle collision. Okay, rigid bodies, you're going to have one more thing. So what type of a collision is ours? Okay, so you take a look at the problem. Okay, you look at the ball. The ball has a pre-impact velocity of 5 meters per second, which is along the line of impact. But what about the pendulum? The pendulum is initially at rest, which means that its pre-impact velocity is not along the line of impact, right? Because it has no velocity to begin with, which means that this is an example of an oblique central impact. Okay, so this problem is an oblique central impact. So let me write this here. Impact problem. Okay, and in terms of the solution strategy, I mean, this is going to be pretty much the same as a direct central impact. There is not much of a change here, but it's good to know, okay, what type of a problem we are dealing with. Okay, so I'm going to copy this figure, and then I'm going to draw three figures which will tell me, okay, what is the situation right before impact, what is the situation during impact, and what is the situation right after impact. Okay, so here is the situation. Okay, so let me draw it 3 times. So here is the first figure. Let me clean this up a little bit. And this line of impact, I have a shorthand notation that I'm going to be making use of. Okay, so line of impact, I'm going to call it as LOI. Okay, and I'll make that change here as well. So this is going to be LOI. Okay, line of impact. Okay, so here is my first situation, which is the situation right before impact has actually taken place. Okay, so this is the first situation, and so this is right before impact. Okay, then I have the impact event itself taking place, and this line of impact direction, I'm going to call it as the normal direction n. Okay, so you watch and see why I'm going to call it as a normal direction n. Okay, then I have the impact event taking place, which I'm going to take these two guys. Okay, I'm going to copy that and then bring them here. Okay, and I'm going to get rid of some of these. I'm going to get rid of that. Let me cut that off and then bring that guy down here. Okay, and what do you know, this ball here, which was initially there, so let me take this ball and then bring it right down there. All right, and so here is the ball. This is right during the period of impact. Okay, so this is right before impact, then right during impact. And let me bring this a little closer here. Okay, and what's happening here is, why have I chosen this direction to be the normal direction, is because of the fact that if I draw a tangential line here at the contact, okay, you see this is going to be perpendicular to the normal line. So this is going to be my tangent line t. Okay, so t is perpendicular to n, and that's why I call it as the normal direction and then the tangential direction. So t and n are perpendicular to each other. Okay, so t and n, so this is during impact, or the impact takes place. Okay, and t and n are perpendicular to each other. And then what happens right after impact? Now right after impact, I'm not sure what's happening to the velocity of the ball and so on. Okay, let me maybe take this creature here. So since I have the tangential direction, I'll just continue using the tangential direction. Let me get rid of this. Let me have the normal direction. That's good enough for me at this point in time. Now I don't know what's happening to the ball right after impact. Okay, so what I'm going to say is the following: this ball, which was traveling along this line of impact, is now going to have a different velocity, okay, right after impact. And I'm going to call the velocity of that ball right after impact as some VB prime. Okay, I don't know what this velocity is, so I'm just going to call it as VB prime. So this is the post-impact situation. And then I have the pendulum. What's the pendulum going to do? The pendulum, as you know, is going to start rotating, right? And since it is having a fixed pivot here, the pendulum at that instant is going to start trying to rotate about this pivot point. So let me draw a circular arc and then hopefully keep it right down there and make it a dotted line. Okay, so what's going to happen is that the pendulum is going to have a post-impact velocity which is going to be tangential to its path right after impact. So this is going to be VP prime. Okay, once again, right before impact, I know the velocity of the ball. It's along the normal direction or along the line of impact. Okay, so this is the line of impact. And if you want, you can write this as the line of impact. This is the line of impact. Then right during the impact, I know that, okay, this is the tangential direction, which is the line that is perpendicular to the line of impact. And these two are impacting each other right after impact. This is right after impact. What is going to happen is that the ball is going to start traveling, I don't know in what direction, because I don't know, I have not solved the problem yet. And then the pendulum, what's the pendulum going to do? The pendulum, as you know, is having a fixed pivot, which means that it's going to start trying to rotate about that pivot. Okay, and which means that the velocity of the pendulum is going to be, the bob of the pendulum is going to be perpendicular to the length of the bar. Okay, so this is a situation that has taken place in our problem so far. Okay, so this is right before impact, the impact event itself taking place, and then this is the situation right after impact. And one more thing that we have seen in problems that we solved on collisions before is that the time period of impact is very, very small. Okay, so assume time duration of impact to be very small. Okay, so let me assume that time t1 is the time right before impact. Okay, t2 is the time right after impact. Okay, and then t1 to t2 is the time duration of impact. Okay, so t1 to t2 is the time duration of impact. Okay, now what am I going to do? I'm going to draw the momentum diagrams at time t1. I'm going to draw momentum diagram of the system at time t2, and then I'm going to draw the impact relevant free body diagram. Okay. Alright, so let me see if I have enough space. I think I have enough space to draw the momentum diagram, so let me bring it out. So here is the situation that I want to bring. I want to take this entire creature here, copy that, and I want to paste that here. Okay, and let's see. Okay, that's pretty good. So when I draw my momentum diagram, there are two things that I want to show. So I'm going to take this and then place that here, and I'm going to take that and I'm going to get rid of that. The first thing is I need to show the direction of the momentum of the ball, right? What is the momentum of the ball? It's going to be the mass of the ball times the velocity of the ball, and the direction of the momentum of the ball is going to be a linear momentum of the ball. Is going to be in the same direction as its velocity before impact. Okay, so this is the situation. Now I also have the tangential direction which I had drawn earlier. So I'm going to bring that. So I'm going to copy that. And I'm going to paste that here. Okay, so this is the tangential direction. So let me draw it as a dotted line. And I'm assuming that this is the positive normal direction, or the line of impact, positive normal, and then this is the positive tangential. There is nothing sacred about saying this is positive tangential. I can say that this side is also positive tangential. There is nothing wrong with that. Okay, I'm just assuming it to be this way. Now the pendulum is at rest, which means that its initial velocity is going to be completely zero, so I can mark that out here. Okay, its initial linear momentum is also obviously going to be zero. Okay, so MP Vp is equal to 0. This is the momentum diagram at t1. At time t1. Then what is the momentum diagram at time t2? I'm going to copy all of these creatures once again. Okay, when you're drawing the momentum diagram, what are the things that you're showing? The only thing you're showing is the linear momentum of the particles of the system. There are particles here, two particles, one is the ball, one is the ball. Okay, then after impact has taken place, what is going to happen to the pendulum first of all? Okay, I know that for the pendulum, right after impact, its impact velocity, the velocity of the bob of the pendulum is going to be perpendicular in the direction drawn, and its velocity is unknown, so its linear momentum is going to be mpvp prime. Okay, so that is the linear momentum of the pendulum right after impact has taken place. What about the ball? I guess I did not want to cut that, but I wanted to cut that off, and in order to remove all of that, give me 1 second. All right, fantastic, that's gone. What about the ball? Okay, the ball is now going to have a linear momentum in some arbitrary direction, so I'm just going to assume its linear momentum is going to be this way. Okay, I don't know what its linear momentum is going to be. Okay, let me, for the sake of convenience, let me take this tangential direction and then bring it down here on the ball. Okay, it's the same thing. Okay, there is nothing different going on there. So this is now going to be MB VB prime. Okay, and so you can immediately see that, okay, hey, I can take this linear momentum and I can split it into two directions. Okay, so look at this. I'm taking the linear momentum and then I'm dropping a perpendicular so that I can find the component of the linear momentum of the ball right after impact in one direction. Then I'm doing the same thing here. I'm dropping a perpendicular and finding the linear momentum of the ball in this particular direction. Okay, so I'm going to call this linear momentum as MB VBT prime because it's in the tangential direction. I'm going to call this as MB VBN prime. Okay, which is in the normal or the line of impact direction. Okay, so this is the situation right after impact has taken place. Okay, and I can do the same thing if necessary for the pendulum bob as well. There is nothing sacred about the directions that I've drawn here. Okay, so I can take this and I can say, okay, if this is the pendulum, I can set it up and say, okay, MPVP prime, I can split it up into a component along the tangential and the normal direction. I'm not necessarily compelled to do it, so I'll just leave it like that. Okay, and obviously, if you look at the pendulum, right, it's going to start swinging. The bob is going to start having a velocity. So the pendulum, I'm going to assume the angular velocity of the pendulum is this way. Okay, so this is omega. So this is the angular velocity right after impact. Okay, and so this is the momentum diagram at T2. I'm just going to copy that and then getting lazy early in the morning. Okay, so this is T2. Alright, so fantastic. We have the momentum diagram drawn. I see something has happened to my 2 there. The number that I had written earlier is something else now. Alright, so this is the momentum diagram at time T2. Then all I have to draw is the impact relevant free body diagram. Let's see if I have some space for that here. Probably not. Okay, so I'm just going to copy these things and bring them down. Okay, again, so let me keep these here as well, but let me bring them down so that I have all my figures in the same place. Okay, and then I also want to draw the impact relevant free body diagram. So how do I do that? Okay, I first draw the ball, and then I draw the pendulum, and then I mark all the forces that are impact relevant. Okay, so impact relevant forces does not include the weight. We have already discussed this when we looked at problem number 1 in collisions. Okay, so go to my solved problem 1 on collisions. You will see what is meant by an impact relevant free body diagram and how I have defined it. Okay, so IRFBD is going to be looking this way. Let me copy my figure from here. I need all the directions and so on, so let me copy that and let me paste that here. I'm going to get rid of many of these things. Okay, I'm going to get rid of that. I guess I was planning to get rid of that. Okay, and then I'm going to take this guy and then I'm going to put that somewhere. I guess I don't know, I can maybe put that here. Okay, now what are the things that are going to happen? I'm going to have a contact force, right? So that's the first thing. The contact force is going to be, this is the contact force of the ball on the bob, so that's going to be Fc, and then this is the contact force of the pendulum bob back on the ball, so that's going to be the force Fc. Okay, then what else would I have? I would also have the pin reactions, right, which means that I have to get rid of this pin here or the pivot and so on. So I'm going to cut off that and completely cut that off, and then rather than that I'm going to have a pin reaction which is OX and OY. Okay, so this is going to be OY and this is going to be OX. Okay, so this is the impact relevant free body diagram, and here is the length of the bob, which is known to us as 1 meter. And just for the sake of convenience, I'm going to take this entire thing and then draw it a little further away, and I'm going to show you something. Okay, okay, I want to take this force Fc. Okay, and then I want to break it up into a component that is along the line of impact, and then in the tangential direction, along the x and the y directions, I'm sorry. Okay, so how do I do this? This angle is 45 degrees here, which means that if I do Fc into a component along the x direction and the y direction, that did not come out straight, but I meant to draw it as a straight line. Okay, so this is going to be one component of Fc, which is in the horizontal direction here, and then I want to do the same thing here, and this is the other component of Fc in the vertical direction. And you can obviously see that the angle here, if I bring this guy, this is Fc, the angle is 45 degrees, so opposite angles are the same, which means that this is going to be Fc cosine 45, and then this is going to be Fc sine 45. Okay, and this is in the x direction and the y direction. Okay, so that's something that you can see. And so this is the impact relevant free body diagram. Okay, so in an impact relevant free body diagram, you look at only the impact relevant forces. Gravity is not an impact relevant force. Okay, so gravity, let me write it properly, apologies, is not an impact relevant force. And why is because the impulse of gravity is very, very small due to the time duration of the impact. Okay, that's essentially what it is, and nothing more than that. Alright, so now I'm ready to exercise all my equations or my options at hand. And very quickly, what are my equations that I have? Okay, so linear impulse momentum equation is the following: m1 v1, this is the general equation, plus integral from t1 to t2, sum of all the forces is equal to m2 v2. Okay, and then the angular impulse momentum equation, this is about a point. That is important. Okay, so this is going to be r1 cross or r cross m1 v1 at some time t1 plus integral t1 to t2 summation of summation of moments about a chosen point dt. This is going to be r cross mv at time t2. Let me get rid of these subscripts here. Okay, so this is the angular momentum at time t1, this is the angular momentum at time t2. These are the vector form, these are the general equations. Okay, so this is something that you might have seen in my previous problems as well. So these are the overall equations, and in using them I have to use them in particular directions very carefully. Okay, so I'm going to start looking at the angular impulse and linear impulse momentum for the bob first. Okay, so let us consider the bob. Let's consider the ball. Okay, I'm going to use the linear impulse momentum in the tangential direction. Okay, so in the tangential direction, what is the linear momentum equation going to be? Okay, so here is the situation. My tangential direction, my positive tangential direction, I'm going to take it to be positive in the way the t direction is drawn here. Okay, so this is my positive tangential direction. Look at this. At time t1, is there any velocity or linear momentum in the tangential direction? There is nothing, right? Because it's only in the normal direction. So that, which means that, and maybe for the sake of convenience, I guess I don't want to bring these figures again and again. Okay, so just take a look at the figures and then see there is nothing in the tangential direction, right? So which means that this is going to be 0. Okay, so this is going to be 0 plus integral from t1 to t2. Are there any forces on the ball? Look at the impact relevant free body diagram. Are there any forces on the ball in the tangential direction? Absolutely nothing. So that's also 0 dt, which tells me that, okay, hey, if I come to the momentum diagram at time t2, what is the linear momentum of the ball in the tangential direction? It is going to be this guy here, mb vb t prime. Okay, so I'm going to put that guy down there. So mb vb t prime, which obviously tells me that vb t prime is equal to 0. Okay, this was kind of expected because of how the problem is designed, but it is still good to know that, okay, the post-impact velocity of the ball is still only in the normal direction. Okay, so which implies that if I had written it this way, so if vb prime, if I had written it as a component in the tangential direction and a component in the normal direction, then I know that vbt prime is 0, so this guy is completely gone. So which means that vb prime is just vbn prime in the en, and I'm just going to call this as vb prime, okay, in the en direction. because I know that there is only one component here. So what I'm going to do is I'm going to strike this off. So make use of this. Okay. So I'm going to make use of this and then come back and then strike this thing off here. Okay. So this thing is now gone. So this is now 0. Okay. And then I can just call VBN prime as VB prime. Okay. So this is the same as MB VB prime. Okay, so I'll just get rid of this again. I just wanted to show you that this is the same as what I had written here. Okay, so now I move on to the linear impulse momentum in the tangential direction. So linear impulse momentum in the normal direction, a normal or line of impact direction. And my line of impact direction was positive this way, so I always have to choose a positive direction to start the problem. Okay, so when I go to the problem, when I look at the ball, there is MBVB. Okay, that's pointing along the positive normal direction. Okay, so this is going to be MBVB integral from T1 to T2. Look at the impact relevant free body diagram for the ball. What are the forces acting? FC in the normal direction, but it's pointing in the negative normal direction. So this is going to be minus FC dt. Okay, and that's about it. And then I go to the momentum diagram at T2. Look at the momentum diagram. MBVBN prime. Positive. Okay, which I anyway call as VB prime. Okay, so I can just say this is the same as MB VB prime, okay, because of what I have just written right about. Okay, so which means that if I'm looking at linear impulse momentum of the ball in the normal direction, this is the equation that I end up getting, and then this was the linear impulse momentum of the ball in the tangential direction. One more thing I could do, since I'm still sitting on the ball, I will do the angular impulse momentum of the ball about the pivot point. Why am I choosing the pivot point? You see, in this problem, I am not interested in the pin impulses. In this OX and OY, who the hell cares about these fellows, right? So, which means that, I want to do angular impulse momentum about a point such that they vanish. And so why not choose the point O, right? So that is the best point to choose. So point O is the best point to choose for angular impulse momentum in this problem. In some problems, it may not be very obvious, okay? So one has to actually go through the process and then see, okay? And here is the linear momentum MBVB of the ball. I need to find angular momentum over the point O. I need the perpendicular distance. Okay, how to find the perpendicular distance? That's fairly straightforward, right? Because I have the length L here. So the perpendicular distance, if I complete this triangle here, okay, this is a 90 degree. I need to make sure that it looks like a 90 degree triangle. Okay, so this is the 90 degree triangle that I'm drawing here. Okay, if that is 45 degrees, this is also 45 degrees, which means that the length here is going to be L times cosine 45. Okay, and likewise here as well. Okay, so if I take this line here and then if I extend this line, and let me take that and put that down here. Sometimes these things get a little tricky, right, as you might have guessed by now. Okay, and then complete this here, which means that this length here is also going to be the same thing, L times cosine 45. Okay, so this is also L times cosine 45. Okay, and likewise if I go, this is L here. Okay, so this is L times cosine 45, and likewise for this FC here as well, if I look at the perpendicular distance, this is all going to be the same thing. Okay, so if I extend this thing here, draw that down there, and then complete the triangle, this is a 90 degree triangle, that's 45 degrees, and then this is going to be L times cosine 45. Okay, so now I'm ready to take the angular momentum about the point O, so for the ball. Okay, so angular impulse momentum about pivot O for the ball. Counterclockwise rotations are treated as positive. That is something you got to be very careful about. Okay, so let's do this quickly. Look at the momentum diagram at T1. Use the right hand rule. Momentum times perpendicular distance. it's going to be MBVB times L cosine 45. If I use the right hand rule, this is going to be a clockwise rotation. Why is it clockwise? Because the fingers of my right hand are aligned with the direction of the linear momentum. My palm is facing the point O. I curl my fingers, my thumb is into the page. Okay, so this is going to be the following. Let me, so minus L cosine 45, or let me write the momentum first. So minus MB VB times L cosine 45 plus integral from T1 to T2, the net moment about the point O. What is that going to be? So that's going to be FC times the distance of L cosine 45. This is going to be counterclockwise, as you can see, if I use the right hand rule. Okay, my palm is going to be facing the point O. My fingers aligned with the force FC on the ball, and if I curl my fingers, it's going to be, my thumb is going to be out of the page, so this is counterclockwise. Okay, so this is going to be FC times L cosine 45 dt. And then I go to the momentum diagram at T2. What is the momentum diagram at T2? MB VBT prime is gone. I don't have it anymore. Okay, right? So this anyway is gone. Let me maybe, I guess it is still possible to draw them in dotted lines. Alright, so that creature is completely gone. So MB VBN prime times L cosine 45 is still clockwise, same as before, but VB prime and VBN prime are the same. So I'm going to write this as MB VB prime times L cosine 45. Okay, so this I'm going to call as equation number 1. Okay, so let me call this as equation 1. This entire thing. I can't do any other simplifications. I can of course get rid of this length and so on. So probably I could do that. And I could get rid of all of these. I could get rid of all of these. I could get rid of all of these. I don't want to do that yet. Okay, so let me just leave it that way. Okay. Then what else do? I go to the bob of the pendulum. Okay, so bob of the pendulum. Okay, so this is my next stop. And then I keep doing angular impulse momentum, linear impulse momentum. Okay, so here I'm going to be a little more smarter. When I do the linear impulse momentum of the pendulum, what is my inclination? My inclination is not to do it along n and t, but to do it along x and y. Because as you see, the velocity of the bob is in the x direction right after impact. So I don't want to break it into components and so on. So this is my strategy here. So let me start off by looking at the x direction. Okay, x direction impact. So let me say that this is positive x direction. I know that the pendulum is initially at rest, so which means that is 0. This is T1 to T2. What are my, go to the impact relevant free body diagram in the x direction, F sine 45 and then OX. Don't forget the pin impulse. Okay, so this is going to be FC sine 45 minus OX dt. Okay, and then this is going to be equal to the linear momentum in the x direction right after impact, which is going to be MPVP prime. Okay, completely useless equation. I can't do much about it. Okay, then I do things in the y direction and I see, okay, linear impulse momentum in the y direction, does it have any use for me? I know that the pendulum is at rest to begin with, so that is 0. Then integral T1 to T2. Anything else that is going on here? I go to the impact relevant free body diagram, OY. Okay, so this means that OY dt. And then I know that the bob of the pendulum, if I go to the momentum diagram, right, at T2, the bob of the pendulum does not have a linear momentum in the vertical direction, so that is going to be 0. Okay, so this is actually good news. This is 0. So this implies that integral T1 to T2 OY dt is equal to 0, which means that the pin impulse along the y direction is 0. Okay, so this is one good thing that I have obtained. Not that it's helping me in solving the problem, as you can see. So I go to angular impulse momentum about the point O. Okay, so when I do the angular impulse momentum, here is what I end up getting. Okay, So I go to the pendulum. Initially it's 0, so there is nothing going on. So initially there is no angular momentum at all. Then I say, okay, T1 to T2. What are my angular momenta terms? I go to the impact relevant free body diagram. Look at this. I'm going to take FC sine 45, take the distance of L. So that's going to be FC sine 45 times L. It's a clockwise rotation. And sine 45 is the same as cosine 45. Okay, so which means that here I'm going to have FC sine 45 times L as the impulse. So this is minus FC times, and I'm just going to say, okay, this is sine 45 times L dt. And then I come here. What am I going to have here? Look at this. MPVP. Okay, that's going to be producing a clockwise rotation about the point O. So the angular momentum due to MPVP prime is going to be clockwise, and so that's going to be minus MPVP prime in the L direction. Okay, so far so good, and I'm going to call this as equation 2. And I can just rearrange this and say, okay, this is integral T1 to T2 minus FC times L cosine 45 dt is equal to minus MP Vp prime times L. I'll just call this as equation 2, where I have said that sine 45 is the same as cosine 45. Okay, so then what am I going to do is I'm going to take equation 1 and equation 2 and add them up together. Okay, so here was equation 1, right? So here was this big guy here. So I have equation 1. So I'm going to copy that and bring that down here. Okay, so here was equation 1 and equation 2. That was equation 1. So add equation 1 plus equation 2. What do you end up getting? Okay, if I add equation 1 and equation 2, I get minus MB VB times L cosine 45 plus integral T1 to T2 minus FC L cosine 45 dt plus integral T1 to T2 FC times L cosine 45 dt. Obviously they're going to cancel off. Okay, so this is going to be minus MP Vp prime L minus MB Vb prime times L cosine 45. Okay, so these are the terms on the left hand side, and these are the terms on the right hand side, and obviously I can cancel these two guys off. Okay, so which means if I clean up, I get the following. Okay, then I'm going to do the substitutions. Okay, MB is equal to 2 kilograms, MP is equal to 1 kilogram, L is equal to 1 meter. Okay, and then cosine 45 is equal to 1 by root 2. After I do all the simplifications and I rearrange my terms, here is what I end up getting. Okay, so after simplification, I end up getting root 2 Vp prime plus 2 Vb prime is equal to 10, and I forgot to mention that Vb was 5 meters per second. These are all given. Okay, so this is going to be equation number 3 for me. Okay, so this is an important equation. So I'm now able to relate the post-impact velocities, but this is not sufficient because I need one more equation, because there are two unknowns, right? I have only one equation. So the other equation is going to come from the coefficient of restitution. Okay, so two unknowns, which is Vp prime, Vb prime. So need one more equation, and that's going to come from coefficient of restitution. So by definition, E is going to be given as the following. Okay, so this is the basic definition. Once again, I have this in my elaborate lecture notes that I have been posting. Okay, so we'll take a look at that. Please do take a look at that. So this is going to be defined as V2n prime, V1n prime divided by V1n minus V2n. Okay, so here 1 and 2 can represent any of the bodies. Okay, so here 1 and 2 represent any of the impacting bodies. Okay, so 1 can be the ball, 2 can be the pendulum. 2 is the, or you can also have 1 as the pendulum and 2 as the ball. Okay, so either one is fine completely. Then V1n prime and V1n. Okay, so V1n and then V1n prime. These are the pre and post impact velocities along the line of impact of body 1. Likewise, V2n prime are the pre and the post impact velocities along the line of impact of the second body. Okay, so this is the general definition of the coefficient of restitution. It's a derivation that I have performed in my lecture notes, so please do take a look at it. I'm going to make use of the essence of this equation. Okay, that's what we need to do here. So for us, I'm going to assume that 1 is the ball and then 2 is the bob of the pendulum. Okay, so which means that if I look at V1n, what is the direction of V1n? And this has to be along the direction of positive line of impact. Okay, so make sure that you know what your positive and negative directions are. So if I go to my line of impact, I see that VB is going to be along the line of impact. So this is for the ball, so this is going to be VB. Okay, so if I zoom up and then come back, so this is going to be VB. What is V2n? V2n is 0 because the pendulum is initially at rest. Pendulum at rest initially. Okay, then I say, okay, what is V1n prime? I come back and then look at my figure. I go to my momentum diagram. Okay, momentum diagram at time t2, look at the ball. What is V1n prime is going to be the same as VBn prime, which I have drawn here, right? And this is along the positive line of impact, so I'm just going to call it as positive VB prime. And then V2n prime, what is that going to be? Okay, for this I'm going to draw the pendulum very quickly here. Okay, so I know that here is the pendulum, here is the pivot. Okay, here is the bob of the pendulum, which we had drawn earlier, and then we have the line of impact direction, which is drawn here. So let me draw it as a dotted line. When I look at the velocity of the pendulum bob, you know, right after impact, the velocity is going to be VP prime, but this is the line of impact direction, which means that I have to take this VP prime and then split it into a component along the line of impact. Okay, and then perpendicular to the line of impact. Okay, so this is going to be VPN prime, VPT prime. Okay, and then I know that this angle here is 45 degrees, which means VPN prime is going to be VP times sine 45, or VP prime times sine 45, which means that V2n prime, because 2 represents the pendulum for me, so this is going to be VP prime times sine 45. Okay, so this is the velocity along the line of impact for me. And so I start substituting. So I have 0.45 is equal to V2n prime, so that is VP prime sine 45 minus VB prime. All of this has to be divided by VB minus 0. Okay, if I rearrange, I get the following. Okay, after doing the rearrangement, I get VP prime minus root 2 VB prime. This is equal to 2.25 times root 2. Okay, so that's typically what I get after the calculations have been done, or the simplifications have been done. This is 4. Okay, so I have now the second equation required for me to solve the problem. 2 equations, 2 unknowns. As I said, I bring the other one, which was here. Okay, so this was equation 3. Okay, copy that and then paste that here. Okay, so 2 equations, 2 unknowns we can solve. Two unknowns. Okay, so solve. And then after solving, here is what you'll end up getting. Okay, so Vp prime is going to end up being approximately 5.13 meters per second. And then Vb prime, because a certain amount of its kinetic energy has been imparted to the pendulum, its velocity is going to be lesser now. Okay, so there's going to be 1.38 meters per second. Okay, and then very lastly, I need to find the impulse due to the contact force. Okay, so impulse due to the contact force. It's very easy to do so because I already have my equations set up. So I'm just going to go back a little bit. Okay, if I go back, I can choose any equation that I want here. I can either choose this equation here because I know, well, I can't choose that equation, I'm sorry, because I don't know Ox, right? So I can't choose that equation until I solve for Ox, which means that my only choice left is to look at, I don't know, maybe I can look at this equation right down here in the normal direction. Okay, so I could take a look at this equation, or I could take a look at equation 1. Either one is fine. Okay, so let me maybe take this equation because we have not used this yet. Okay, so I'm going to copy this and then bring it down here. This is from the ball. You can take the ball or the bob. It is the same FC. Okay, it is just that the direction is different for each of them. So I'm going to cut that off and maybe cut that off as well. Bring this guy down here, cut that off, and then if I rearrange my terms, I'm going to get integral t1 to t2 fc dt is mb vb minus mb vb prime. Okay, this is the ball, which means that if I do the substitutions, t1 to t2 fc dt is going to end up being the following. Okay, so after all of this has been done, this is approximately going to be 7.25. Look at the units, Newton seconds. Okay, this is the impulse of the impulse of on the ball. Okay, due to the contact force. Alright, so it's a fairly long problem. As you can see, the length of the problem was exacerbated by me explaining many of the steps in between, taking my time to draw the figures and so on, but I hope this has been a useful exercise. Once again, the idea is very simple. Okay, I go back to my first figure that I had drawn here somewhere. Here is a pendulum, here's the ball. Throw the ball, ball hits the pendulum, ball moves somewhere, pendulum moves somehow. How is this happening? What are the velocities taking place? Okay, so this is a collision event. We've discovered that, okay, this is an example of an oblique central impact. Okay, and in this situation, right after impact and right before impact, I draw the momentum diagrams. These are the situations before and after impact and during impact. Once I draw the momentum diagrams, as you've seen here, then I also draw the impact relevant free body diagram, which is shown down here. Once I have that, then all I do is I'm using the linear impulse momentum and the angular impulse momentum for each part of the system. That is, a ball is a part of the system, the pendulum bob is a part of the system. So I use angular momentum, linear momentum for the pendulum, I use angular momentum, linear momentum for the ball, and then I start mixing and matching terms and saying, okay, what is going to be useful, what is not going to be useful. Hopefully this is going to give me at least one useful equation, which is what it ends up giving me here after all this. And then I have to make use of the idea of coefficient of restitution, which is kind of an experimental thought. Okay, it is, in my opinion, not the greatest way of solving a problem by bringing out this number, which is sometimes dependent on so many other factors. material factors and so on, but this is one way of solving the problem. Okay. So I bring the coefficient of restitution, I make use of the definition, go through all of this, and then end up with the other equation, and then I solve for it. If I have to find the impulse, I can make use of any one of the equations that contains the impulse and then find out the answer. Okay. Thank you for your patience. I really appreciate it. Take care of yourselves. Bye-bye.